Let's get started. So this slide that we talked about last time, and I just wanted to go over it again. So listed the the different stage or phases after meal, and how glucose is produced, and which and how different tissues utilize glucose as energy fuel. Again, here we specifically talk about the glucose, right? But of course, fatty acids and ketone bodies also important fuel during the fasting stage. So, for example, the absorptive phase after meal, so 0 to 3 hours after meal, we usually use the exogenous fuel, right? Particularly, the dietary carbohydrate as energy. So most of actually all of the tissues, right, in our body, able to utilize glucose for energy, or primarily use glucose as energy during this first phase. And brain, of course, glucose is a major fuel for the brain. And 4 to 18 hours after meal, and phase 2 actually start, in the fasting stage, right? So we actually undergoing the fasting stage. So 4 to 18 hours, our body start to utilize stored energy. So glycogen is the first stored energy that our body uses. So during this time period, we primarily break down the glycogen. Of course, liver glycogen, right, is the main sources of circulating glucose. So, and again, most of the tissues all utilize the glucose as energy, except liver, muscle, and adipose tissue use a limited glucose for energy, just try to spare glucose for brain and red blood cells. And brain still, again, utilize the glucose as a major fuel. And as the fasting goes longer, 18 to 48 hours after meal, if we still, don't eat food, then the hepatic gluconeogenesis become an important sources of circulating glucose, right? Glycogen, again, is depleted after 18 hours fasting. And during this time period, phase 3, 18 to 48 hours, gluconeogenesis become more active and produce glucose, right, from non-sugar precursors, but still utilize glycogen. But again, glycogen sources become limited, right? We almost use all of the glycogen for energy. So all the other tissue except again, liver, muscle, and adipose tissue have a very low rate of glucose utilization, but the brain is still be able to utilize glucose for energy. And if starvation goes longer than 2 days, then the glucose, for energy, particularly from gluconeogenesis, become limited, right? We have a limited capacity, particularly liver gluconeogenic capacity kind of decrease. So kidney then become more important, the gluconeogenesis, right, to provide glucose. And in the meantime, we know that fatty acids, right, it's released from adipose tissue and become important energy sources for other tissues, particularly muscle. And brain, we know, cannot utilize fatty acids, right? So fatty acids go to the liver and generate ketone bodies. So ketone body, ketogenesis, become very active after 2 days starvation and become a very important energy source for brain and of course other tissue as well. So more than 2 days starvation, brain is able to still use glucose but very limited, but now become utilize more ketone bodies for energy. So I just wanted to remind you again, and this table specifically talking about the glucose utilization, right? So and not including much the fatty acids as an energy fuse. So again, if we go back to the last slide that I mentioned in last class, after again 24 hours the starvation, fatty acids being released a lot from fat tissue, right, and become most important, the energy fuel for a lot of tissues, and ketone bodies also produce a lot from the liver after 2 days of starvation. Fatty acids are the important fuels for muscle, right? And ketone bodies are an important fuel for brain and muscle as well. Now let's talk about the fuel utilization switch. We have a little bit more information about the post-absorptive phase, right? The 4 to 18 hours after meal, so our body enters so-called post-absorptive phase. So blood glucose is maintained by the breakdown of glycogen, right? Liver glycogen particularly, and brain accounts for 50% of glucose utilization. So 50% of the circulating glucose, are used up by the brains, and the utilization of the glucose by other tissues is slowed down. And the other important thing is that the glucose is only mostly partially oxidized, right, to produce lactate, and will not completely oxidized. So lactate can be saved for synthesis of a new glucose. And after 18 hours, I mentioned many times that liver glycogen is depleted, so we don't have a liver glycogen store anymore. So we started using the other metabolic pathway activities, for example, gluconeogenesis. So to make a glucose to maintain blood glucose level, and in the meantime, fatty acids being released from fat tissue for alternative energy fuels. So what happens? And after 24 hours starvation, the gluconeogenesis become more active, right? Because of glycogen stores, is depleted. So gluconeogenesis become more active compared to glycogen breakdown activities, and kidney gluconeogenesis in kidney is also more active, and liver gluconeogenesis activity become decreased. So brain, in terms of glucose metabolism, and brain is the only tissue that completely oxidize glucose even under the fasting condition. Only when very long-term starvation and brain also partially oxidized glucose. And also during the starvation, the amino acids being also released from the protein breakdown or protein degradation. And amino acids are the very important precursors for gluconeogenesis. And fatty acids, ketone bodies, like I just all mentioned, I think I did actually finish this slide, right? Sorry. And this slide will just quickly go through, and again, the concentration of the different energy fuels in the plasma during the prolonged starvation. You can see the glucose definitely goes down, right? The glucose level in the circulation dropped significantly, and also let me see what else. And amino acids also decrease, right? In the circulation, and lactate and also decrease. So basically glucose, amino acids, and lactate levels are significantly decreased during the starvation in the circulation. And the other alternative fuels like fatty acids, triglyceride, and glycerol actually goes up. And particularly you see the ketone bodies, right, in a huge increase in the circulation during the fasting. So you wanted to understand the changes of energy fuel concentration during the fasting condition, right? Fatty acids and ketone bodies increase, and triglyceride levels also increase, and the glucose, amino acid, lactate are all decreased. So here's the question: why lactate and amino acids actually decrease in the circulation during the fasting? Where do lactate and amino acids go? During fasting? Right, to liver for doing what? Gluconeogenesis, right? Yes. So lots of lactate and amino acids actually, being used for gluconeogenesis. And lactate basically go to the liver, right, through the Cori cycle, and for making glucose. And amino acids and mostly go to the kidney for gluconeogenesis, right? Okay, now let's talk about the fuel utilization switch. There are actually two types of a switch between fat and fasting condition. So under the fat condition, our body utilizes glucose as the main energy fuel, right? And we have a limited utilization of fatty acids or fat. And during the fasting, I forgot the other source. So during the fat condition, we utilize mostly carbohydrate, like glucose, for energy, in type of energy fuels switch. And the other type is switch is the sources of energy fuels, right? During the fat condition, we utilize mostly dietary carbohydrate as the energy, right? And during the fasting condition, our utilization of glucose become limited, and we utilize more fatty acids or ketone bodies for energy. And in terms of sources, switch, and we utilize more stored or synthesized energy, right? Energy fuel during the fasting condition. So two type of switch: sources of energy fuels and type of energy fuels switch. So this something can explain by so-called Randle cycle. So Randle cycle is named for Philip Randle, who actually described this phenomena in 1963. So sometimes we also call the Randle cycle is glucose fatty acid cycles. I kind of switch back and forth depend on the fasting condition. So, for example, under the fat condition, we have a lot of glucose available from the diet. So the high causing the increase the blood glucose level, which leads to increase the insulin levels and decrease the glucagon levels. And because of this hormone levels change, that will promote the storage of fatty acids and storage of carbohydrate as a glycogen, and suppresses the mobilization of fatty acids and utilization of fatty acids, right? So under the fat condition, we tend to store energy more as the glycogen for carbohydrate or triglyceride for fatty acids, and we utilize more prefer utilizing more carbohydrate glucose as energy, and we have very limited capacity to utilize fatty acids under the fat condition. And during the fasting, because our blood glucose goes down, right? We don't have dietary glucose available, so that will causing decrease insulin and increase glucagon, and the ratio of insulin to glucagon change, right? And this change will stimulate the utilization of fatty acids to promote fatty acids mobilization and oxidation, but we suppresses the storage of fatty acids and also suppresses utilization of glucose, right? And this is the more, but just using the different, diagram to show you the fuel utilization switch during fasting condition. So under the fat condition, we have high levels of glucose, and muscle can take up glucose for oxidize. So oxidation for ATP production, and adipose tissues also can utilize glucose, right, for energy. But during the fasting condition, because of glucose utilization is limited and decreased in the adipose tissue, so the glucose utilization can inhibit the fatty acids release from the adipose tissue. But during fasting, again, because of glucose utilization is decreased or limited, that will actually stimulate, fat mobilization. And so you have lots of fatty acids released from fat tissue and utilized by skeletal muscle. So the fat utilization and glucose utilization, they can kind of, interregulated. One activities up and will causing the other, sources of energy utilization is decreased or downregulated, right? And this is the mechanism how glucose utilization will inhibited by fatty acid utilization under the fasting condition, right? So again, we already know that the fat utilization and glucose utilization, you can only choose one, right? And depend on the physiological condition. So under the fasting condition, right, we have lots of fatty acids available that basically is from lipolysis, right, in adipose tissue. So circulating fatty acids increase. The body cells can pick up circulating fatty acids and oxidize for energy production. So if you're probably familiar with this pathway, right? Fatty acids being uptake. CD36 is actually the transporter, fatty acids transporter, located on the surface of muscle cells and other type of cells. So and here I think we use the muscle cells as an example. Fatty acids can be taken up by muscle cells through the CD36 transporters. And first of all, fatty acids need to be activated, right, before it can be oxidized to long-chain acyl-CoA. And CPT1 is, okay, maybe I wanted to point out. So the light green area indicates the mitochondria, right? The orange is the cytosol of the cells, and blue represent the circulation, right? So once the fatty acids being activated in the cytosol and need to be transported into the mitochondria by CPT1, right? CPT1 regulate fatty acids transporter, and fatty acids once it's entered the mitochondria and undergoes beta oxidation, right, for ATP production. And during this oxidation process, there's a lot of acetyl-CoA molecules generated, right? So we're causing increased acetyl-CoA levels in the mitochondria under the fasting condition. So the acetyl-CoA then be transported out of the mitochondria in the cytosol, and for the the malonyl-CoA production, right? But under the fasting condition, and this pathway will not be very active, right? This is the adipogenic pathway, lipogenic pathway, right? You still remember? So under the fasting condition, again, this pathway will not be active, but the acetyl-CoA level will be increased, and this is the strong acetyl-CoA is a strong inhibitors of pyruvate dehydrogenase, right? If you still remember. So the pyruvate dehydrogenase, if it is inhibited, that will inhibit the pyruvate oxidation, right? Further oxidation. So this is one point, how fatty acids oxidation will inhibit the glucose oxidation. And also because of the acetyl-CoA levels increase, that will also increase the citrate levels, right, in the cytosol. And citrate is strong inhibitors of glucose hexokinase, and also the other two enzymes that in the glycolytic pathways, right? So the glycolysis glucose metabolism glycolytic pathway is strongly inhibited because of the acetyl-CoA levels increase, because of this citrate levels increase, right? Does that make sense? So there are actually 3 points in the glucose oxidation pathways are inhibited because of increased acetyl-CoA levels and increased citrate level. Right. So this is sort of a mechanism how fatty acid oxidation increase can decrease glucose oxidation. Right. Any questions? Again, when we have high activities of fatty acid oxidation during the fasting condition, well, acetyl-CoA will be generated, right? A lot of acetyl-CoA will be generated, and acetyl-CoA is the strong inhibitors of pyruvate dehydrogenase activities, and which is important enzyme, right, to further oxidize pyruvate. And also because of citrate levels is increased, which converted from acetyl-CoA. So citrate is also the strong inhibitors of the key enzyme in the glycolytic pathway, right? So all these are the 2 important intermediates, right? The levels are increased during the fasting condition when fat oxidation is increased, and these key intermediates again are the strong inhibitors of the key enzyme in the glycolysis and pyruvate dehydrogenase, right? So that is again the mechanism how fatty acids oxidation increase during fasting can inhibit glucose oxidation, glucose utilization. Again, try to remember these 2 key factors, right? Key intermediates, citrate and acetyl-CoA, right? Levels increase. Now, how about under the fat condition when we utilize a lot of glucose? How this would inhibit fat utilization? So similarly, you can see this pathway, right? One is fatty acid oxidation, and the other one is the glucose oxidation or glycolysis. So when glucose level increases during fat condition, right, we get a lot of glucose from the diet. So glycolysis pathway will be active. So this pathway will active and also generate a lot of acetyl-CoA under the fat condition, and this acetyl-CoA majority of mainly from the glucose oxidation, right? And if you still remember, this is the pathway, the lipogenesis pathway, right? When we have a lot of carbohydrates available, and we try to convert the carbohydrate to fat, to fatty acids. So this is the lipogenic pathway. So acetyl-CoA generated from glucose oxidation can be converted to citrate and across the mitochondrial membrane to cytosol and for production of malonyl-CoA, right? And ACC is the key enzyme to catalyze this reaction, if you still remember, right? So again, here the malonyl-CoA is the key intermediate, right? So under the fat condition, when we have higher activities of glucose oxidation, we generate a lot of malonyl-CoA. So malonyl-CoA levels are increased in the fat condition. And if you still remember, it is how malonyl-CoA regulates fatty acids oxidation. CPT1, right? So CPT1 is a key enzyme that regulates by malonyl-CoA. So when we have a high levels of malonyl-CoA, can inhibit CPT1. And then inhibit fatty acids transporter from cytosol to mitochondria for beta oxidation, right? So, so this is again as the mechanism for how glucose oxidation inhibits fatty acids oxidation in the fat condition. Again, malonyl-CoA is a key molecule that mediate this inhibition, right? Any questions? Okay, so now let's talk about regulation. We know, switch, right? Fuel utilization switch from carbohydrate to fat when we undergo fat through the fasting switch, and we also know that the fatty acid oxidation activity can inhibit glucose oxidation, vice versa. So how, and then we also know the detailed mechanism, right, intracellularly, but how, overall, how this switch is regulated. Or in other words, how our body know when to switch the metabolic fuels. So here is all things that are involved or regulates this kind of switch. First is the hormone levels, right? We mentioned the insulin and glucagon levels are the key hormones that regulate this type of a switch. And the enzymes that control the metabolic activities, right, or metabolic pathway like glucose oxidation and fatty acids oxidation. And lastly, the transporters, right, glucose transporters and also, the fatty acids transporters. So all these kind of things that involve the regulation of a fuel utilization switch. This diagram, I bet you guys all understand, right? We talked so many times. So just on the top part, actually, the pathway that and tissue that involved in the regulation of the glucose metabolism under the fat condition, and bottom part is the fasting condition, right? How glucose metabolism in the tissue regulated, and all the regulation that involve the four major tissues like muscle, adipose tissue, liver, and pancreas. And the purpose of all this regulation is to maintain blood glucose level, right? So I divided into different stage, or different state. So the fat condition, when we ingest the carbohydrate, causing increase the blood glucose level, right? And this will stimulate pancreas and causing increased insulin and decreased glucagon. So insulin to glucagon ratio is increased, and this increase will promote the glucose transport into muscle and adipose tissue, right, by GLUT4, you still remember. And in the liver, also the major tissues that regulate blood glucose level. So under the fat condition, lots of glucose actually goes into the liver by GLUT2, and GLUT2 is not an insulin regulate transporter, right? It's actually glucose level regulated transporters. So GLUT2 goes into the liver under the fat condition because of insulin levels high. So insulin basically promotes storage of the carbohydrate as a glycogen in the liver. So glycogen synthesis pathway is increased and also promote the conversion of carbohydrate to fat. So lipogenesis pathway is also activated by insulin. But the other catabolic pathways of glucose need to be shut down, right? We don't need to use the stored energy. So glycogen breakdown pathway is decreased, and gluconeogenesis pathway is also decreased. So the glucose production from the liver is inhibited in the fat condition. So all this work together, the four organs, tissues work together to maintain blood glucose level under the normal range, right? And in starvation, we have a lower glucose, right? Our blood glucose level goes low, and that will inhibit insulin secretion and stimulate glucagon secretion. So we have a lower insulin to glucagon ratio under the fat condition. And because of a lower insulin, so the glucose uptake into muscle and adipose tissue will be also decreased, right? And in the liver, because of less glucose being taken up in to the liver, so we have less glucose available for glycogen synthesis. So glycogen synthesis pathway will be decreased, and lipogenesis pathway activity also decreased, right? But we need to maintain blood glucose level. So liver is very important organ that produce glucose either from the breakdown glycogen or from the gluconeogenesis, right, to make glucose and release to circulation to raise blood glucose level. So now I'm going to talk about the exercise, right? Something that's different, from the fat fasting condition in terms of hormonal level, actually. So fat and fasting condition, the main changes in hormone levels actually are the insulin and glucagon, right? But during exercise, the catecholamine are the main hormones that change during the exercise. So the liver, muscle, and adipose tissue are the main targets of catecholamines. For example, adipose tissue, catecholamine can stimulate the lipolysis, stimulate fatty acids release, and the muscle, in the muscle, catecholamine also can increase glycogen breakdown and amino acids catabolism, right? So, breakdown of protein. So catecholamine break down glycogen and also break down the protein to release the amino acids. And liver, catecholamine does do is to increase the gluconeogenesis, right? So all this three targets tissues of the catecholamines work together to raise fatty acids levels and also blood glucose level, right? So during the exercise, because of catecholamines levels increase, so stimulate the fatty acids release from fat tissue, and also stimulates a glycogen breakdown and gluconeogenesis in the liver, so release glucose, right? So you will so this slide it talk about the regulation of liver glucose production. So under which physiological condition where you expect the liver will produce glucose and release glucose into the circulation. Fasting, right? So fasting, and maybe you guys can just discuss for a few minutes about this. You know, how is liver glucose production regulated by insulin-glucagon ratio, right, in a fasting condition, right? Why don't we just take a 10 minutes break, right? We'll come back like 35. Let's move on. So I guess this is pretty straightforward, right? So under the fat condition, because of the plasma glucose levels lower, so we have, did I say the fasting? Okay. I'll just talk about the fat condition first, right? So under the fat condition, right, we have a high levels of glucose, so high insulin and low glucagon, and that will promote, regulate these three different metabolic pathway glucose differently. So glycogen will be glycogen synthesis pathway will be stimulated, and glycogen breakdown pathway will be inhibited, and gluconeogenic pathways also inhibits, right? So that will lead to decrease the production of the liver glucose during the fat condition. And fasting condition, again, because of the change in ratio of insulin to glucagon, decrease insulin and increase glucagon, and you regulate, the pathways of glycogen synthesis and gluconeogenesis differently, right? Downregulate glycogen synthesis and increase the upregulate glycogen gluconeogenesis and glycogen breakdown pathway. So, and the net effect of all this regulation and of a glucose metabolism leads to increased liver glucose production. And here I'll just mention that insulin and glucagon actually has opposite regulatory role, right? Insulin basically, is a catabolic hormone that means promotes synthesis of glucose, like a glycogen synthesis, right? And decrease the catabolic metabolism, like glycogen breakdown pathway will be inhibited by insulin, and glucagon just does the opposite. The glucagon basically promotes the degradation or catabolism of the glucose, right? It promotes glycogen breakdown and inhibits glycogen synthesis and also stimulate gluconeogenesis. So once you have this kind of idea in mind, then it will be very easy to, understand if we're asking which enzyme, the key enzyme in which pathway will be up or down regulated, right? It will be very easy to understand. And also we have, I guess, two tables, right? And listed, the transporter hormones and pathway, the key enzyme, just for you to review and try to remember, again, the key enzyme in different pathways and how this key enzyme or that specific pathway being regulated by different hormones, right? And it also involves the glucose transporters. Now let's talk about something related to metabolism disease. Diabetes, right, is a very common, metabolic disease. And we know there are two types of diabetes, right? Type 1 and type 2, and the actually cause is different. So type 1 diabetes basically is caused by a little or no insulin secretion because of a beta cell, kind of dysfunction. The reason is still not very clear why, type 2 diabetes patients will have some problem with the pancreas, beta cell. So this type of diabetes is insulin dependent diabetes. That means if we give them insulin back, right, to supplement patient with insulin, then can cure diabetes. But the problem is that this type of patient that you rely on the insulin injection almost every day. I mean, it's not easy to handle with. And type 2 diabetes is caused by we call it insulin resistance. Insulin resistance means that your insulin action or insulin function is reduced. You have if you compare normal to a type 2 diabetes patient, give them like same amount of insulin, and the normal person will respond to insulin very well, right? To reduce blood glucose, and type 2 diabetes patient will not have that effective insulin. So the insulin resistance, that means insulin action is reduced. And the early stage of type 2 diabetes patients actually even have a higher levels of insulin, right, in the blood, because of body try to produce more insulin to compensate the reduced action, right? But when the later stage, when type 2 diabetes progress, the insulin actually production is decreased. Somehow eventually the pancreas or beta cell also went the failure, right? So called beta cell failure in the later stage. So later stage of type 2 diabetic patient also have a decrease or lower insulin level. So you need to give insulin supplementation and to the later stage, type 2 diabetic patient. So in terms of treatment, if it's early stage of type 2 diabetic patient, we can encourage them to change their diet and do more exercise. Sometimes you can give anti-diabetic drugs, but for the later stage, then you will also need to give them insulin therapy. So kind of mechanism, hopefully when we learn all this, glucose metabolism, hopefully we understand the mechanism, right, for behind the type 2 diabetes. So type 2 diabetic patients not only have the blood glucose control problem, but also lipids, right? Problem. So as I mentioned, the adipose tissue, liver, and muscle are the, of course, the pancreas, right, are the main metabolic tissue that involved in the regulation of the lipids and glucose and lipids metabolism. So in diabetic patients, this tissue also have some kind of problem or changes. So let's talk about adipose tissue first. So the main defects in the adipose tissue in diabetic, type 2 diabetic patient is they have a decrease or lower GLUT4 expression, right? And they also have problem with the translocation of a GLUT4 from inside of cell to the cell surface in response to insulin because of insulin resistance, right? So insulin cannot efficiently, stimulate translocation of GLUT4 to the cell surface. So all this together will causing the decreased glucose uptake, right, by the fat tissue. So you have a lower glucose uptake. That means your more glucose will remain in the circulation, right? So I draw that kind of diagram, and this just represents a part of the adipose cells, right? And on the adipose cell surface, there is insulin receptors and also a GLUT4 transporter. Insulin binds its receptor, right, on the cell surface and can transduce insulin signal, and there are actually two. You can have a multiple signal pathway, right, depending on how insulin regulates. Then in adipose tissue, we're focusing on the two main signaling pathways. The one is regulate glucose metabolism, and the other one is regulate lipid metabolism. So in the type 2 diabetic patient, because of insulin action is reduced, right, insulin resistance, so insulin cannot efficiently stimulate GLUT4 translocate to the cell surface. So you have a less GLUT4 on the cell surface and for glucose transporter, right? And so you have a more glucose staying in the plasma and lower levels of glucose inside of cells, right? And again, a type 2 diabetic patient also have a problem with the lipid metabolism. So similarly, we know that insulin inhibits the lipid, the lipolysis, right? If you still remember. So insulin basically inhibits lipolysis. Does that make sense? During fat condition, when we have a high insulin levels, and we also have a lower lipolysis, right? Under fat condition, we don't need the fatty acids for energy. So so the lipolysis process usually is inhibited during the fat condition. Insulin inhibits the lipolysis pathway. So when we have a lower insulin activity or low insulin action, and this inhibition will be reduced, right? So that means in diabetic patient compared to normal people, they will have higher levels of HSL, right? Because of insulin actions reduced. So that will causing increased lipolysis in the fat cells in the type 2 diabetic patient. So you have more fatty acids being released into the circulation, right, in the diabetic patient. So you have higher levels of circulating fatty acids. And if you still remember, the fatty acids levels in the circulation is the main driver, right, of ketogenesis. So when they have a high levels of fatty acids in the circulation, then ketogenesis will be increase, right? Sorry, I changed for some reason. So, and LPL, if you still remember, is the secreted from fat tissue, right? And hydrolyzed triglyceride in VLDL and chylomicron, right? Break down triglyceride. So, and LPL is also regulated by insulin. So, when insulin actions decrease, so LPL production, secretion will also decrease. So you have a lower LPL, and this will causing less triglyceride being hydrolyzed, right? So triglyceride actually remain in the circulation, cannot be break down, right? To release fatty acids. So and finally I go back here. So because of increased fatty acids level, that will drive the ketogenesis, right? So ketone bodies level in the circulation also increase in the type 2 diabetic patient. So in general, type 2 diabetic patient, because of insulin resistance, insulin action is reduced, so all will affect the glucose and lipid metabolism. So the consequences of the this impaired metabolism, that type 2 diabetic patient will have a higher blood glucose levels, higher fatty acids levels, and higher ketone bodies level and triglyceride level in the circulation, right? Does that make sense? So that's why, the ketogenic, the type 2 diabetic patient also have a ketoacidosis, right? Any questions? Right? No. Now that was something happening in the adipose tissue. Now what about the muscle? So muscle also express the high levels of GLUT4, right? And GLUT4 is also regulated by insulin and in the muscle. So actually GLUT4, muscle GLUT4 regulated by two things, right? One is insulin and the other is a muscle contraction, right? So insulin, similarly, insulin resistant and muscle cell were not able to transport the GLUT4 to the cell surface. So cell surface GLUT4 also reduced in the muscle cells in the diabetic patient. And the other important thing is that the mitochondrial function in the muscle cells is somehow decreased, right? And you know that the muscle, because of the large mass, right? So muscle uptake glucose and oxidized fatty acids play a very, very important role in whole body metabolism. So if muscle has some problem, cannot take up glucose, that definitely will contribute high levels of glucose, right? And also if muscle cannot oxidize fatty acids because of mitochondrial function decrease, so fatty acids will also remain in the circulation, right? And so this altogether contribute to the diabetic syndrome, right? Increase, high levels of glucose and high levels of fatty acids in the circulation. And the liver. So liver, we know as the can uptake glucose under fat condition for making glycogen, right? Or also convert to fatty acids. And under fasting condition, liver actually produce glucose, right? By breaking down glycogen and also gluconeogenesis. But under the diabetic patient, they have actually higher levels of gluconeogenic enzyme activities. That probably related to the high levels of glucagon in the diabetic patient. So because of insulin actions decrease, so kind of similar, relevant to the low level of insulin, right? And glucagon level actually increase in the type 2 diabetic patient. So that will causing low insulin to glucagon ratio decrease. So that kind of mimic, the fasting condition, right? So the gluconeogenesis will increase in the type 2 diabetic patients. That will contribute more blood glucose level, right? To raise, even higher blood glucose level. And fatty acids, because of fatty acid levels increase in circulation, so liver picks up fatty acids and converts to the triglyceride and causing fatty liver disease, right? So that are something, or dysregulated metabolism in the type 2 diabetic patient. And the actual cause is still not very clear. I mean, why, how insulin resistance being developed in the diabetic patient in the type 2 diabetes is still not very clear. A lot of people actually study this, area. Still lots of questions unresolved, right? Any questions about this disease? Okay, so insulin resistance or some other kind of concept that people also talk about in the metabolism field is called metabolic inflexibility. So that means, something need to be changed, like a fuel utilization switch, right, during the fat and fasting condition that the normal people can do, but the insulin-resistant patient or diabetic patient, they have an inflexibility. They are not able to switch easily. For example, in the insulin-sensitive or lean people under the fat condition, when we have a higher glucose level and we stimulate insulin secretion, right? So insulin can, and all the tissue in the normal people, they are sensitive to insulin. So insulin can regulate all the metabolism to increase the glucose utilization and inhibits fatty acids oxidation, right? But in the insulin-resistant or obese subjects, individuals, under the fat condition, right? They also increase blood glucose level and increase insulin level, but because of insulin sensitivity to in all the tissues, insulin sensitivity is actually decreased, right? So they not be able to promote efficiently the glucose utilization. Okay, I think that's all we have for this unit. Okay, we have a few minutes, right? Can we talk about exercise, utilization, and exercise? So this will be different from the fat and fasting or full intake, the fuel utilization, because of the hormonal levels, right? It's different. So what you need to know in this unit is what is the aerobic or anaerobic exercise, right? The concept. Aerobic exercise basically is the moderate intensity, and it's kind of a long duration exercise, right? And anaerobic exercise is a high intensity and a very short-term exercise. For example, marathon is type of aerobic exercise, right? So during this type of exercise, that our body will need oxygen, right? And that it also involves the oxidative metabolism of both glucose and fatty acids. And aerobic exercise does not need oxygen, right? And does not involve the mitochondrial oxidative metabolism, right? And second thing that you need to know is the exercise intensity. So we usually use the oxygen consumption, the maximum oxygen consumption, to measure the exercise intensity. For example, when we do a intense exercise and we need more oxygen, right? We need more energy, need to produce more ATP, so we need more oxygen for oxidation to produce the ATP. So oxygen consumption is linearly associated with the exercise intensity. And third is the respiratory quotient, RQ. So RQ is the concept that is actually the measurement and to estimate, what kind of energy fuel that muscle use for energy, right? Whether muscle uses more carbohydrate or uses more fat as the energy fuel. This type of things is kind of important, when you and then sources of energy fuel for exercise. So during exercise, muscle can use typical energy fuel that we use during the resting condition, right? Carbohydrate, fatty acids, right? And in addition to fatty acids, muscle can also use the creatine phosphate. Have you guys heard about this, right? So as an energy. And again, what type of fuel that muscle use depend on type of exercise, right? And finally, the fuel utilization in aerobic and anaerobic metabolism. So we're going to talk about what kind of, energy fuel that muscle use during aerobic exercise versus anaerobic exercise. They are all very different, right? Let's see. And more thing you need to know is the fuel utilization during post-exercise recovery period. When you finish the game, exercise, then you need to have your muscle recover, right, for for energy storage or some other things. So the metabolism during this specific post-exercise recovery period is also pretty unique and specific. And muscle adaptation in response to training. So trained versus untrained individual, they have a very different, capacity, right, in terms of oxidation of the energy fuels. So our body usually will adapt to training. So training usually can increase the oxygen consumption capacity. And lastly, the carbohydrate loading, intervention to increase muscle glycogen. So muscle glycogen is very, very important for the performance of exercise. So we wanted to have more glycogen being stored in the muscle and get ready for exercise, right? So how can we increase the muscle glycogen load? That is going to talk about a different approach, right, for the carbohydrate loading to increase the muscle glycogen. Okay, so I think I'll just stop here, just give you kind of, brief view.